Okay, so this one is waves and light and diffraction and interference patterns. So in this case, we talked a little bit about it, the fact that the light goes through the slits, and diffraction means that the light spreads out in patterns a little like this from each of the two slits. Where there are two peaks, which are represented by the lines here, there'll be constructive interference. Where there are two troughs together, there will be destructive interference. So that's the situation, and on the back line there will be a bright band at the center, where, because the distance from each slit is equal at the center, so wherever the distances are equal, then you'll get peaks coinciding and you'll get a bright band on the wall at the back, the screen at the back. So the first bright, or the 0th bright band, I guess, where n equals 0, or where n equals 1, sorry, and we'll get to that in a second. Where the difference between the wavelengths, the distances, is 0, you get a bright band, and then the first bright band will be at this point y. So in between it'll be dim, and it will, the intensity actually is, so the intensity is a maximum there, decreases there, increases there, and so on. So if you're graphing the intensity, you'll get something that looks a bit like a sine wave as you go across there. That's the light intensity, with that way being higher intensity. So as you're traveling, in this case, we've got, sorry, I've kind of obscured it. Let me see whether I can do something about that. Okay, nice clean diagram again. So I've kind of obscured. We've got the angle theta, we've got the distance d, which is the distance from the middle of the slits to our point that we're interested in. We've got the distance little d between the slits, which that might be a little bit difficult to see, 2 by 10 to the minus 3 meters, so 2 millimeters. 2 millimeters, 2.0 by 10 to the minus 3 meters is the distance between the slits. This distance here, we're told in part 3 of the question, is 20 centimeters, or 0.20 meters is that distance. So in other words, we've got a screen with 2 slits in it, we've got another screen 2 meters behind it. Sorry, 20 centimeters behind it, 0.2 meters. And over here we've got a point light source. It could be a laser or just a small point of light that's emitting light. So the light really actually is spreading from that point, and then it's re-spreading, as I showed before, from these points. So we're getting diffraction, bending around the corner of a surface or an edge. And so we're going to, as I said before, have a bright band here and a bright band here and another bright band up here and another bright band further up here. We want to know the distance to the first one in a minute, but starting, this experiment ideally requires the use of monochromatic light, one color, one wavelength of light, commenting on Y. The reason basically is that if the constructive and destructive interference depends on the number of wavelengths, and for different colors of light the wavelengths are different. So the bright band for blue will appear in a slightly different place to the bright band for red. So it'll be quite difficult to actually spot the maximum, because it will be different maxima for different colors. So if we just use a laser or some other source of monochromatic light, then we get much clearer bands than if we use white light with its multiple wavelengths. If green light with a wavelength of 531 nanometers, and that's a particular laser that I've used quite a lot in the lab, 531 nanometer laser. What is the frequency? Let's scroll up a bit. So the frequency, remember that we've got the equation that says, oops, sorry, this is question 2. Question 1 we answered with text. We've got V equals F lambda, but for all kinds of electromagnetic radiation, including visible light, v is just equal to c, the speed of light. So in this case, c equals f lambda. We're asked to find what's the frequency, so we'll rearrange that to make the frequency of the subject. F equals c on lambda. Now c, we know, is 3 by 10 to the 8 meters per second. Lambda, hang on, we're in nanometers, not meters. So we've got lambda equals 531 nanometers. Nano meaning 10 to the minus 9. So it's 531 by 10 to the minus 9. But to put it in proper scientific notation, 5.31 by 10 to the minus 7 meters. So a bit messy. 5.31 by 10 to the minus 7 meters is the actual wavelength expressed in SI units and scientific notation. 5.31 by 10 to the minus 7. And that ends up giving us, and I've put down my piece of paper, that ends up giving us 5.65 by 10 to the 14 hertz. Now, hertz is not a plural, it's a singular. You can't have a single hertz in this case. But we have 5.65 by 10 to the 14 hertz, so 5.65 by 10 to the 14 cycles per second. We could write hertz as seconds to the minus 1 per second, but we have a particular unit that we use for frequencies called hertz, and that's 10 to the 14. 10 to the 12 is giga, so it's 565 gigahertz would be the frequency of that particular light. So all right, we know the frequency of our light. Just kind of, that was a piece of just reminding ourselves of one of the things about light. Now the destructive interference, let's have a look. So part 3, we're asked if d, the distance from the screen to the double slit, is 20 centimeters, find the distance between the central bright band and the next bright band above it. We have an equation that we talked about in the lecture, which is that for a maximum, let me see, n lambda equals d sine theta. So n is just a number, it can be 1, 2, 3, etc. N lambda equals d sine theta, where d, as you'll see from the diagram above, is the distance between the slits here, 2 by 10 to the minus 3 meter, and theta is the angle here. We've got y and d. Now it turns out that if we go back to our cos again, opposite, SOHCAHTOA, sine theta equals y over big D. So we can use that. So if we actually substitute that into this equation for sine theta, we end up with little d and y over big D. So n lambda equals that. Now we're just going to use n equals 1 because that's for the first bright band. If we wanted the second bright band, we would use n equals 2 and so on. So anything multiplied by 1 is just itself, so we actually don't have to worry about the n. So we end up with lambda equals dy. Now that's not a differential, that's just a little d times a y over d. But we're interested in the distance y. If we go up to our diagram again, we're interested in the distance y between straight ahead and, in other words, the first the 0th bright band, the central bright band, and the first bright band above it. So that's the distance we're interested in, is y. So we'll rearrange this to make y the subject. Y equals lambda times big D over little d equals the wavelength we know is 5.31 by 10 to the minus 7 meters. Big D is 20 centimeters, 0.2 meters. Little d is 2 millimeters, 2 by 10 to the minus 3 meters. and overall that's going to give us 531 or 5.31, again because that 2 and that 2 are going to cancel, but there's a difference of 2 orders of magnitude. It ends up being 5.31 by 10 to the minus 5 meters is the distance between those two bands. Now that's very tiny, 10 to the minus 5 meters. It's on the order of hundredths of millimeters. It's about 53 nanometers. So it's not very large, this interference pattern. In this particular setup that we've got with this color of light and this separation of slits, the diffraction pattern is really quite tiny, but that's actually what the answer is for that one.